Hey, everybody. It is Monday, November 9th. As you can see here in the AIM today, today's focus is going to be on how we can apply the free body diagram technique to ATWOOD'S machines. Now, you may remember me mentioning this in the meeting on Friday if you were there. If you weren't, then I guess you'll be hearing this for the first time. But since my computer is now broken, I no longer have the ability to edit these videos. So I'm going to be trying to do this entire thing in one shot. So I apologize if my throat gets dry and I start coughing, or if I make a mistake and have to erase it. The transitions here are going to be a little sloppy. I hope you bear with me. I hope you all know I'm trying my best to make this as painless for you as possible, but you should all probably understand that the likelihood of this being an absolute disaster is significantly higher than the other videos. So with that joyous note, let's get started. So as you can see here, the main focus for today is going to be talking about how we can use the free body diagram technique for ATWOOD'S machine problems. But at the end of the video on Thursday, where we did these problems when you have to use the free body diagram to solve a statics problem, this problem in particular was the one we did, I asked you to submit an answer for the last two parts. And so I want to start off by going over those. And so in this problem, if you remember, you had to basically do the math. We had to solve for the weight of the ball, and then we had to solve for the tension in the two strings. And now what's happening in this problem is they've changed the situation. And the situation has changed so that now rope 1, which has a tension T1, or FT1 as we've labeled it, is now oriented horizontally like this, where FT2, which is over here, notice is still at the original angle it always was at. And part D, after saying this left-hand string is now attached to the wall, it says indicate whether T2 is now greater than, equal to, or less than the value you reported in part C. And it says to justify your answer qualitatively without using equations or calculations. I think the main thing that you have to realize to answer this question is what each component of the force does. The goal, like the real point of the X components, is to cancel each other out. That's what they do. They cancel each other out. They provide horizontal stability because they cancel each other out. The vertical forces here, like in this original situation, as you saw when you wrote the equation from the free body diagram, they cancel out the weight. So what's the real difference now that FT1 is not at an angle of 53 degrees, but now is totally horizontal? The key difference now is it no longer has a vertical component. So what that means is the vertical component of FT2 is the only thing acting vertically, and that's the whole ball game. What I wrote here, which is hopefully similar to what you wrote, is the tension in the second rope, FT2, must be greater in this case. That is a fact. Since the first rope is directed purely in the horizontal direction, the vertical component of the tension in the second rope, FT2Y, is the only force, or force component really, to counter the weight of the object hanging from the ropes. Since the first rope no longer bears any of the weight, the Y component of the second tension force, FT2Y, must be equal to the weight. So let's be clear about that. Since the first rope no longer bears any of the weight because it no longer has a Y component, that means the whole Y component of the second tension force, FT2Y, must be equal to the weight. If you remember, when we solved for the weight of the ball, because it was a half a kilogram, we got 4.9 newtons. So what I wrote here is since the Y component of FT2 now has to equal a number, 4.9 newtons, the weight, which is larger than the entire value of FT2 originally, which was 2.95 newtons, then FT2 must be larger now. If you're not sure what I'm talking about with these numbers, let me just go back. In this problem, we calculated that the weight of this ball was 4.9 newtons. And when we solved for FT2, we got that it was 2.95 newtons. So now what we're saying is a force that was 2.95 newtons now has to have just one component that's going to be equal to a number that's bigger than that, almost twice as much. And so the idea here is, because now just the y component has to be bigger than the entire force used to be, the whole force now has to be bigger too. Take a second to pause this video here and write that down, and when you hit play, we'll move on. Okay, now let's take a look at part E. Part E says determine the new vertical component of FT2 without using equations or calculations. Justify your answer qualitatively. Well, I already kind of went through it in the last part here, but the y component, the vertical component of FT2 here, which is FT2y, has to be equal to the weight. We already know what the weight is. It's 4.9 newtons. And so the answer I wrote for part E, I know I told you to write just one sentence, but I'm trying to explain this to you here, is the y component of the tension in rope 2, FT2y, is now 4.9 newtons. It's got to cancel the weight. So since the first rope is directed purely in the horizontal direction, the only force to counter the weight of the object is the y component of the tension in the second rope, FT2y. Since FT2y is the only force acting up in the positive y direction, and the weight, Fg, is the only force acting down in the negative y direction, those forces must equal in magnitude, since the net force in all directions in this situation is 0. To make a long story short, it's got to cancel the weight. That's it. Take a second to pause this video here and write that down, or amend your explanation, add anything onto that. And if you didn't make any mistakes with your explanation, and if you wrote exactly that, then just advance this video ahead a few seconds to sort of go over the pause time. But if you didn't get a chance to write that down, pause this video here and write that down. And when you hit play, we'll move on. Okay, so let's just summarize a couple of big things here from this kind of problem. So the first thing that we need to say is about the components. This is a big note here. The purpose of the horizontal components is to cancel each other out, while the purpose of the vertical components are to bear the weight of the object. They got to be canceled by the weight. That's like the whole point of them. Also, and we said this on Thursday, but just to sort of really drive it home, ropes oriented more vertically will have a larger tension because their y components are bearing more of the object's weight. That should really say bearing more of the object's weight. While the x components are going to have to cancel each other out. So if the x components are always equal, but one has to take on more of the weight, then its tension is going to be bigger. Right? The x components are always equal. That's a crucial fact about these problems. Take a second to pause this video here and write that down. And when you hit play, we'll talk about the ATWOOD'S machine. Okay, so I also mentioned this in the second meeting on Friday, but this is a crucial fact regardless. The ATWOOD'S machine has been on the AP test free response section 3 out of the 6 years the test has been given. It is an incredibly important problem. And so it's really important that everybody understands this back and forth, left and right, up and down, through and through. You need to be able to solve one of these in your sleep. The obvious question here is, well, what the hell is an ATWOOD'S machine? And an ATWOOD'S machine is a system of cables and with a pulley to demonstrate force concepts. And I'm sure what you're thinking here is like, whoa, 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 don't give me too much detail here. I'm going to show you a picture of it in a second. But let's just write one more thing down about it here, because this is an important thing to know too. The ATWOOD machine has 2 varieties. which either show the masses just hanging or with one resting on a surface. When they're just purely hanging, that's just called an ATWOOD'S machine. I usually refer to the one where they show the object sitting on a table as the tabletop ATWOOD'S machine. And we'll talk about those in the video tomorrow. But an ATWOOD'S machine looks like this. That's it. It's just a pulley with a rope, 2 objects hanging from the rope. That's it. And the objects have different masses, and the thing is going to move. And so our job here is to use free body diagrams to analyze the motion of the objects. I'd like you to take a second, though, to pause this video here and write that down. And when you hit play, we're actually going to look at one of these ATWOOD'S machines in action. Okay. Every single year in class, I jump up on the table and I show an ATWOOD'S machine in motion. And it looks a little something like this. So I get up on there, I hold the thing, and I say, all right, guys, I got these 2 blocks, and I hold them just like this. And I say, what do you think is going to happen to the blocks? Somebody says something cute, like, they're going to move. And then I say, okay, well, how are they going to move? Which direction are they going to move? Let's start with that. Which direction are they going to move? And usually the answer is, well, the one that's lower is going to go down, and the one that's higher is going to go up. Some people disagree. They say, no. I think the one that's higher is going to go down, and the one that's lower is going to go up. And I say, okay, well, there's obviously only one way for us to find out, so let's find out. And then I let it go, and we see what happens. And as you can see here, what happens is nothing. Nothing happens. It does not matter what their height is relative to each other, which you can see in this situation. Now, as you will notice, I hope, what is important here is that these masses are exactly the same. And so the obvious question here is, well, what if the masses are different? And if the masses are different, then what you notice, let's maybe do it like that. If the masses are different, I hope you can all tell that the blue one is now bigger than the red one. If the masses are different, then it moves. Everybody look at those dots. What do you notice about those dots? What does that tell you about how the objects are moving? Oh, they're getting farther and farther apart as time goes by. These things are accelerating. That's an important point. Point number 1. These things are accelerating. Notice it went down like this. That makes a lot of sense. And it also actually makes sense regardless of their heights. Notice I showed the red one lower than the blue one, and they went like this. But that also works if I show the red one higher than the blue one. That makes like a ton of sense. The blue one is heavier. It's always going to go in the direction of the heavier one, right? And the last thing is, when the masses are not the same. So let's summarize what we saw. We saw when the masses are the same, it moved. When the masses are, or excuse me, that's the exact opposite. See, I would cut this out, but I can't now. When the masses are the same, it doesn't move. When the masses are different, it does move. And when the masses are even more different, now I just put in this lighter one, then it accelerates more. And let me just run through all of them so you can see. Same mass, nothing. Different mass, Decent acceleration, but still kind of slow. Huge difference in the mass, accelerates fast. That makes sense. But of course, masses don't cause objects to change their motion. And so this has nothing to do with mass per se, but we'll get to that in a minute. So let's sort of summarize so far our little observations. Observation number one. When the two masses are the same, there's no motion. When the two masses are different, there is motion. And when the two masses are more different, there's more motion. And let me be clear. When I say motion here, you all saw it. It was acceleration. And so when we say more motion, we really mean more acceleration. Now, of course, as I hope everybody sort of saw where I was going with that last point here, mass is not something that could cause an object to move necessarily, or accelerate at least. Force is. But the difference in the mass obviously has something to do with it. If we had to describe that as succinctly as we could, then we can say here, in an ATWOOD'S machine, a difference in the gravitational pull on each block is what causes the motion. In other words, it's a difference in the weights. These are very important observations in terms of like writing the whole thing down and being able to think very carefully about this kind of problem. So take a second to pause this video here and write that down. And when you hit play, we'll talk about some more important details. Okay, so let's write down a couple of really important notes, which are all going to come back into play once we get into some problem solving. The first note, and we already saw this actually, is that when the two masses are different, they accelerate in the direction of the heavier mass. That is completely intuitive. The heavier mass goes down. So I'm going to write heavy. It goes down. And if it's light, then it goes up. That makes complete sense to me. I hope it makes complete sense to you. Additionally, and this is really like the most important point when we get to solving these problems, the cable, or the rope, however you want to put it, connects the two masses, causing them to act as one system with a total mass which is equal to the sum of their masses, m1 plus m2, with the same acceleration, because the cable is taut, or in other words, has a tension. The fact that these objects are connected by a rope means that they move together, essentially, is what we're saying here. And so that means the accelerations are equal. And lastly, an important point to realize too, and we talked about this for the last problem with the bird feeder, the tension is constant throughout the rope. It's the same at all points in the rope, because we assume massless ropes here. Now, sometimes they say that, sometimes they don't, but if they don't say it's a massless rope, you can assume that it is. And it says here that means there's only one tension when there's one rope. And that's another important point as well. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, So before we actually get into the problem, because these problems are a bit lengthy, then we can at least say something about each individual object when they're connected to the rope. So we have in this problem two objects which are connected to a string. And it looks something like this. And what we really want to ask is, what is the free body diagram going to look like for each individual object? What forces act on this mass? Take a second to pause this video and think about that. What forces are acting on this mass? Think about it for like 30 seconds, and when you're done thinking, hit play. Okay, so it should be obvious to everybody, based on what we've said so far and just based on what we've said this year, that these objects are definitely going to have a weight. And so we'll draw that as an arrow going down and we'll label it FG. And because these objects are connected to a rope, there's a tension acting on the objects as well. And that force of tension is going to act up. And an important note here, and we'll label that FT, by the way. An important note here, which I hope is clear to everybody, but we'll say it anyway. How FT is going to compare to FG depends entirely on the motion of the block. So we'll say how FT compares to FG depends entirely on the motion of the block. And you know what? Let's even go ahead and put some more detail on it. Let's say if the acceleration is up, notice this is kind of like the question I asked you about the elevator problem. If the acceleration is up, which force is going to be bigger? How can you tell? If the acceleration is up, that means the F net is up, which means the tension is going to be bigger than the weight. And lastly, we can say here, if the acceleration is down, then that means the weight is bigger than the tension. This is really, 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 really important. So I'd like you, if you haven't already, to write this down and think really hard about these notes, because this stuff is really, 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 really important. And when you hit play, we'll actually just jump right into a problem. All right, so here it is, pretty basic ATWOOD'S machine. I'd like you to sketch that diagram in your notes. It says here, based on the information given in the problem, determine the acceleration of the system and the tension in the rope. So the actual text of the problem, if this was in a textbook, would say something like, as shown in the figure below, a 10-kilogram a 10-kilogram block is attached to a rope, which is, wrapped around a pulley. The other side of that rope is connected to a 4-kilogram block, as shown in the diagram. Based on the information shown in the figure, determine the acceleration of the system and the tension in the rope. And so, as I think the aim suggested here, the way to do this is to draw the free body diagram. And so that's what we're going to do. Let's just keep in mind, though, that there's not a whole heck of a lot that they give you. And just to save space on the other slides, I just want to write here, let's just say for the purposes of keeping everything together, and it really doesn't matter what you do, but let's just say for the purposes of keeping everything together, let's say M1 is 10 kilograms and M2 is 4 kilograms. Usually, if there's a diagram, I will label it from left to right. Left is 1, right is 2. Other textbooks or online sources you may see will label the bigger one big M and the little one little m. The AP test will actually do that sometimes as well when there's 2 problems involved. And if it's on the AP test, like an AP test question, follow the convention they show you in the problem. If they say this object has a mass of uppercase M and this one has a mass of lowercase m, then keep those symbols. But otherwise, just number them however you want. Just make sure you're staying consistent is the point. And we'll also say here, the only other thing we know, which I hope you realize is going to be relevant to the problem here, that G is 9.8. And we're looking for the acceleration and the tension. And I hope everybody realizes, although you might not, so that's why I'm telling you, the reason why I'm writing the knowns over here is to save space on the slide after this, number 1. But number 2, the first stuff we're going to show, really all the way up until we plug the numbers in, is going to be general. That means for any ATWOOD'S machine, these equations will apply. Okay, so the first thing you got to do for these problems is you have to draw the free body diagrams. And you have to draw a free body diagram, which is separate for each object. And so let's just go ahead and do the first diagram for the first object, which we labeled M1, which is 10 kilograms. So we'll draw our dot representing this 10 kilogram object, and we must ask ourselves the question. Let me go back to the picture, actually. Is the 10 kilogram object going to accelerate up or down? Is the 10 kilogram object going to accelerate up or down? It's going to accelerate down. It's the heavier object. So over to the side, remember, not connected to the diagram, has to be off to the side. I'm going to show an arrow showing me the acceleration, which is in fact down. Why is it important for me to think about the fact that the acceleration is down? Well, we have to draw these diagrams to a rough scale. So that means I'm going to write the weight here, which is FG1, or you could actually label that M1G if you want, up to you. And we have the tension going up, but the tension has to be smaller because the thing is accelerating down. And that's it. That's our free body diagram for the 10 kilogram object. I'm going to draw a dividing line here. And we'll say that this is for the second object. So this is for our object M2, which is equal to 4 kilograms. And here's our free body diagram. So we've got our 4 kilogram object. And it should make sense to everybody. And I'm going to go back to the previous slide. If the 10 kilogram is coming down and it's connected by a rope to the 4 kilogram object, whoops, 4 kilogram object's coming up. It has to. And so we'll say here, off to the side, that the acceleration of this one is up. Now, a super important thing about these problems, which we already wrote down in the note, but you realize, which you might not realize has significance for these diagrams, is that there's only one rope and the tension in the rope is constant. Your free body diagram has to reflect that. So notice the length of the arrow that you draw for the 10 kilogram object has to be about the same as the length of the arrow for the 4 kilogram object. These things, I want to be very certain that I'm emphasizing this appropriately. These arrows have to be about the same length. Now, as I mentioned, and you will see this very shortly, the AP test gives you grid spaces for these. It'll be super easy to make them the same length. And if you have a ruler and aren't trying to draw this on a computer, it'll be a lot easier for you. But keep that in mind. These tensions are equal. The diagram has to show that. And then we have to show the weight of the object. And notice we're going to want to be very careful about making this one pretty small, because it's definitely got to be smaller than the weight of the other object. And it's definitely got to be smaller than the tension. So we'll just show that like this. FG2 or M2G. And that's it. Those are our free body diagrams. Let's just write off to the side here because this is important. Note, FBD's free body diagrams must show FT with the same size. And I'm going to write in parentheses here, arrow length. That says must up there, by the way. It's kind of getting cut off. Okay. So, as I hope you realize from the statics problem with the bird feeder, when you write an equation, or when you draw a free body diagram, the point is to write an equation from that free body diagram. So now that we've written our free body diagram, we got to write an equation. And I hope you also realize that when you write an equation, you take M1A and you set it equal to the forces going in the direction of the acceleration and subtract the forces going opposite the direction of the acceleration. So we have M1A equals the forces going in the direction of the acceleration, which is the weight. Notice I don't want to mess around substituting that out, so I'm just going to write M1G. You should start to do that from now on. Writing FG is kind of worthless for these problems. Whenever you need to write down the weight, you should probably just write MG. If there are two objects, you'll have to write M1G or M2G, but you might as well just write MG. And then we have that minus the force going in the opposite direction here, which is the tension. And there is the equation for the free body diagram for M1. For M2, I'll just go ahead and do this one down here. We have M2A, the net force, is equal to the forces going in the direction of the acceleration, that's Ft, minus the force going in the opposite direction, which is M2G. And those are my equations. If you didn't already get a chance to write this down, you definitely want to write this down, because this is what the AP test is going to ask you to do. They are not going to say calculate the acceleration. They are going to say, part A, draw the free body diagram. Part B, what are the equations from the free body diagram? Part C, derive an expression for A or Ft or, whatever. So you want to make sure you're able to do that. Okay, so looking at this equation, I hope, because you guys are old, number one, and good at math, number two, I hope you realize that if I'm going to take these two equations and solve them both for the acceleration, there's a pretty easy way to do that, right? I mentioned this when we were doing the bird feeder problem, but this is an important point to realize here. This is a system of equations problem. You have two equations, you have two unknowns, the acceleration and the force of tension, and you need to solve this thing for one variable at a time. There are a lot of ways to do it. We said the accelerations are equal. We could solve both equations for the accelerations and set them equal to each other. That doesn't really help us solve for the acceleration, though, because we just got rid of it by setting them equal to each other. But we also said the tensions are the same, though, right? So can't we just solve the M1 equation for tension and set the M2 equation for tension and then set them equal to each other? You could, I guess. But there's a much easier way to do this. Look at the equation. What do you notice? There's something really convenient about the way these equations are written for this particular problem that makes it really easy to solve another way. What you hopefully notice, which you may not, but it's important to recognize if you didn't notice, you may want to write this down. In these problems, based on the fact that the objects are always going to accelerate in like the same direction, I guess, but really opposite directions from like your reference frame, one goes down, the other goes up, is that for one, the tension is going to be opposite the acceleration, and for the other, the tension is going to be in the direction of the acceleration. And that means in these equations, the tension in one of them is going to be negative, and in the other one, it's going to be positive. And that means you can always solve these equations for the acceleration by addition. You add the equations. You definitely saw that in math before. So what we'll say here is to solve these equations for A, we'll add them and solve. So when I add equations, I just literally write them right on top of each other. So I got M1A equals, remember, I'm just going to go back just so you see it. M1A equals M1G minus FT. And then for the other one, I had M2A. Oh, whoops, I went the wrong way. I have M2A equals FT minus M2G. Okay, cool. So on the left side, I have M1A plus M2A. And I guess because this is the first one, let's not even do it. You see how this is an FT that's not positive? Geez. You see how this is an FT that is positive and this one is negative? They cancel. Bingo. We don't have to write FT minus FT because you know that's going to cancel anyway. So that's that. So now we look here and you see that one's positive. So let's write that first so we don't have to go nuts. M1G. And then that one has minus sign in front of it. So we're going to say minus M2G. Cool. And we want to solve this for A. I think the key thing to realize, though, I hope everybody sees this. On the left-hand side, you see how there's an A in that one and an A in there? And then on the right-hand side, there's a G and then a G. We could factor. So I'm going to factor out the A. I got A times M1 plus M2, and that's equal to G times M1 minus M2. And now to solve this for A, I got to divide both sides by the sum of the masses. Whoops. Divide both sides by the sum of the masses. And so when you wrap that up and you do the math here, it cancels from this side. So we just get A equals G times M1 minus M2 over M1 plus M2. Cool. Now, we're going to come back to this because this is like a really super important point. But the way that equation looks is actually really, really important. Notice on the top, we had M1G minus M2G once you redistribute the G. What does that mean? M1G, what is that? Minus M2G, what is that? It's the difference in the weights. Bigger difference in the weights, because it's in the numerator, bigger acceleration. We already said that. And notice in the denominator here, we have the total mass. They move as a system, as one, with the total mass of M1 plus M2. All that stuff bears itself out in this equation, and that makes this pretty cool. Let's just go ahead and finish up the math here. I'll do that on the next slide. So my equation, I'm just going to rewrite that here, was A equals G times M1 minus M2. By the way, I wrote that on the other slide separate without the numbers because that's always what the equation is going to look like for an Atwood's machine, at least assuming that M1 is the heavier object. And now I can plug in the numbers. Here, I got G is 9.8 meters per second squared times M1 minus M2. So that's going to be 10 kgs minus 4 kgs. And then that's over 10 kilograms plus 4 kilograms. 10 minus 4 is 6, obviously. And then 10 plus 4 is 14. And what I think is super important to notice and like a good way to think about it, I do not want you to write this down. I'm just saying this for now. You should really think about the acceleration as being equal to G times the ratio of the difference in the masses over the sum of the masses. If you think about it as being equal to G times this ratio, first of all, it's easy to put in your calculator. I'm just going to put 6 over 14, get a number, and then multiply it by 9.8, piece of cake. And when you do that math, you should get for the acceleration 4.2. Notice if you end up getting an answer here that's bigger than 9.81 or 9.8, you made a big mistake. So be careful with that. 4.2 meters per second squared. Cool. And the problem also asked us to solve for the tension. And so we want to make sure that we are able to solve for the tension also. And the key thing to realize here is that in order to solve for the tension, we need to just use one of the equations that we had. So I'm actually going to go back here. You could choose M1. You could choose M2, the equation for M2. I don't really care. For no reason at all, I'm just going to pick the equation for M1. Whatever. It doesn't matter. If you pick the equation for M2, you'll get the same number. But we'll pick the equation for M1, and the equation for M1 says M1A is M1G minus FT. And so to solve this for the force of tension, I got to add this over. So I got FT equals, and then I have M1G minus, because I got to subtract that over, minus M1A. And I don't want to plug a number in twice if I don't have to. So I'm going to write this as FT equals M1 times G minus A. G minus A. That look familiar? Sort of like an elevator problem. Isn't that cool? So I got 10 kilograms, my M1. And then that will be times 9.8 meters per second squared minus the acceleration that we just found, 4.2. And when you do that math, it works out pretty easy because the mass is 10 here. 9.8 minus 4.2 is 5.6. And so you just multiply that by 10, you get 56. Bingo, bango. And that's it. Now, what I hope everybody realizes, considering like what I was just showing you before on the internet, is that you can find some of these simulators like this one or this one, which allows you to control the masses, and you can play around with these things. Now, this same simulator in particular only lets you change the masses between 0 and 2, but if you literally just Google ATWOOD'S machine simulator, you can find probably one that will let you play with the mass more. Notice I typed in ATWOOD'S machine simulation, and if you just look, this one says modified ATWOOD'S machine, so it might be on the table. I didn't show you the tabletop one yet, though, but I guess we'll go back to this one to show you that. Remember when I said there's a modified one that I call a tabletop ATWOOD'S machine? It looks like this. We're going to get to that in the next video. But if you look around hard enough, and if I find it again, I'm going to post it. I don't want to waste any more time in this video. But you'll be able to play around with the numbers, so when you're trying these on the homework, you can tell if your numbers are correct. Now, I think this video is already getting pretty long, but just so I don't make it too long because I can't cut it down and change the time anymore, I just want you to answer one more question about this problem before we go. Suppose the masses in the previous problem were changed from 10 kilograms and 4 kilograms to 20 kilograms and 14 kilograms. So instead of being 10 and 4, the 10 was changed to 20 and the 4 was changed to 14. Would the acceleration of this new system be greater than, less than, or equal to the acceleration of the old system? And why? Take a couple minutes to pause this video. Take a look at the equations. Think about it. Don't calculate it. I want a conceptual reasoning answer here. So why, conceptually, might it make sense that the acceleration would be greater than, less than, or equal to the acceleration of the old system? Take a couple minutes to think about this here, and when you hit play, we'll go over it. Okay, so there are a lot of things that we can say here. An important point I want to make just very quickly here before I show you like a whole series of notes is that the equation for the acceleration of an ATWOOD'S machine looks like this. And we are getting into a part of this course where, like you saw how we just drew the free body diagram, we essentially came up with the equation for this on our own from those free body diagrams and solved for everything. That's what we're going to be doing for a little while here. And what I want everybody to realize is when you are doing this and solving for the acceleration, the equation for the acceleration is always going to take the form of A equals F net over M. And so what that means is whatever is in the numerator of your acceleration equation, well, that's going to be F net. And so here, the F net is the weight difference. And M1 plus M2 here is your total mass. And both of them have an impact on the acceleration. So let's say first, the new acceleration of the system is going to be less than the acceleration of the old system. It's going to be less for a very good reason. So let's go through the whole thing. The equation takes the form of A equals F net over M. According to Newton's second law, A is F net over M. Since the net force in an ATWOOD'S machine problem is equal to the difference in the weights of the objects, and the difference in the weights of the objects are the same, the net force acting on the system is the same. Notice, with a 10 and a 4 kilogram mass, the difference in those masses was 6 kilograms. And here, with a 20 and a 14 kilogram mass, the difference in the masses is another 6 kilograms. So when we multiply that difference in the masses by 9.81 or 9.8 for this class, we're going to get the same number. So A is directly proportional to F net, but the F net is the same. So that's not going to make a difference. So then I guess the question really is here, well, then why are we saying the acceleration is less and not the same? Well, it's because the net force isn't the only thing that affects the acceleration. The mass does too. Since the masses of the objects are larger in this case, the total mass, and thus the total inertia of the system, is larger. And so essentially, we're using the same force to try to move more mass. And so since the acceleration of the system is inversely proportional to the mass of the system, and the mass of the whole system, the two objects together, is now larger, the acceleration of the system is going to be smaller or less than the acceleration of the old system. That's the idea. Take a second to pause this video here and write that down, because this point is like super, super, super important. All right, guys, if you wrote that down, that's going to be it for today. Now, I understand that this last part of this, talking about like what the numerator represents and what the denominator represents, might be a little confusing, but I want to put that out there now because we're going to go through a bunch of these problems here in the next week or so. And I want you to keep in mind that that's always going to be true and look out for that, because it's going to make understanding these problems a lot easier. But with that, if you wrote that down, then that's it for today. Have a good one, everybody.